Hello. So good evening. Thanks for coming. I appreciate you being here on an evening session, right? Our first session of summer thermodynamics. So, in case you missed sort of the initial, I don't know if I sent it in an email or just put it up as an announcement in my courses. This, even though it's our first lecture, we'll be starting with the material that's lecture 4 if you're following along with the notes or with, looking at the thermal shorts or the videos that I've posted on YouTube in the past. Actually, one second, just before I would like to get the live transcript going, just in case someone wants that. So we'll get that up too. So this is technically lecture 4. The first 3 lectures are very definitional. So I don't want you to have to listen to me read you definitions because I think it's boring for me and it's boring for you. So we're going to start looking at material, but it would probably behoove you, would be a good idea to look through the notes that I posted for the first 3 lectures, or maybe check out some videos that I've recorded, because this will technically be lecture 4. So just a little bit about myself. So my name's Mike Schertzer. I'm a professor here in mechanical engineering. Class will run, I think technically it goes from 6:30 to 9:40 on SIS, although SIS is down, so I couldn't double check this morning. So obviously you're here in the right Zoom link, so you found us. That's good. Office hours, I did send out a link and I saw that 3 out of 5 students had filled it out. So we'll be able to pick a time for office hours that works for people. Just a little bit about myself. So I grew up in Toronto, so just across the lake from Rochester. Moved here in 2013 when I started working at RIT. This picture's probably a couple years old now, but this is my 3 girls. So currently 12, 10, and 4.5. So she does one of these for 4.5, and so she's waiting on 5. Here they were at the zoo today. We like to play board games. So this is a game called Stuffed Fables. We've kind of evolved from this game into Gloomhaven mostly. We've also played some Funkoverse. This is kind of a fun game, and the kids love Harry Potter, so that's a good one. Last summer, I went maybe 20 years of my life owning one guitar, and then last summer in the pandemic, I bought 3 other guitars, but one of them was for my daughter. Right? I bought a 12-string and an electric guitar to go along with just my 6-string acoustic that I've had. Another thing that I try to tell all my classes is that I like to read, but obviously, or well, maybe not obviously, but I find it hard to find time to read anymore because there's always so many things going on. So instead, I like to listen to audiobooks now. And if you subscribe to, well, you don't have to subscribe because it's free, to Overdrive or Libby, I think is their like sister app. Because you have a New York State mailing address, if you live at RIT, then at some point during the year, then you have access to the New York Public Library. So when I first moved here and heard about this, I was like, well, the Monroe Public Library here doesn't have a ton of selection, but then getting access to the New York Public Library, they have a ton of audiobooks. So it's kind of cool if you're into audiobooks, don't pay for something like whatever the Amazon one is called. Just get it for free, right? Sometimes there's a waiting list, but it works out pretty good. Like I said, I grew up in Canada. Where I did my undergraduate degree is a place called McMaster University. This is in Hamilton, Ontario, which is maybe an hour outside of Toronto. I did a 5-year program, but it was not a co-op program. It was a double major in engineering and business, or commerce, they called it there. So we did a double major, so a lot of all the required courses from this business degree, plus everything that we took in engineering. There's no co-op option, but I did have some opportunity to get some really good summer work. So I worked at Chrysler in Windsor, making the full-size vans for 2 summers. So that's Windsor's right across the river from Detroit. It's actually north of Detroit because of the way that geography works. But it's a little funny, right? Or it's south of Detroit. I'm sorry. So when we were talking, I'd hear people talking on the phone, and they'd, maybe they were American, but they were talking to people how to get to the plant, and they're like, oh, if you got like a compass in your car, it's pretty cool because you're going to Canada, but you're going south, right? Because if you ever look at Ontario, it kind of swoops down there. So I worked there for 2 years. And then not long after I left, that plant closed because they moved it to Tennessee because they got better tax treatment, right? So then after that, I worked as an undergraduate researcher for 3 summers, looking at some heat transfer problems. I did my master's degree at the same university. So we were looking at how to cool electronics in space, which, at first blush kind of seems like a funny problem, right? Because it's very cold in space, right? But electronics generate a ton of heat in a very small area. And as they get hotter and hotter, as the temperature increases, then the performance of those electronics go down. So even though there's this infinitely large heat sink, you want to be able to push that heat as fast as you can. If you think about it like an electrical circuit, you want to reduce the resistance between the hot chip and the cold exterior. And some of the best ways to do this is by boiling some kind of fluid. You get very good heat transfer, very low thermal resistance when you do that. Now, when we use a boiling loop here on Earth, it works pretty good because you put the hot thing low, right? That boils something like water. Water turns to steam, which is less dense than water, right? And it moves up, and that's where you put your condenser, where things get cold. It turns back into water, and it drifts back down, right? But that's all based on gravity, right? Now, in space, that's a problem because, gravity is very low in space, if not zero, right? So instead, we have to use different forces that maybe you don't think about too much here on Earth. So we started to use capillary forces. So here, where we were adding heat, in order to pump that liquid, we used a porous alumina, which is a type of ceramic plate. So that worked a little bit like the wick in a candle. So the way a candle works, right, is that the flame melts some of that wax, and then the string in the candle acts like, it's like a straw. It's the capillary forces, the holes in the string are pulling that wax up. So most of what you're burning is wax, even though you do burn the string a little bit at a time, but you burn the string a lot slower than if you just lit a string on fire, right? So this was the same sort of thing. So because we were using this boiling heat transfer, we could remove a lot of heat reasonably well, even in microgravity. Now, the work that I was doing was terrestrial, but we did have a PhD student who was doing parabolic flights with this type of, which is super cool. So he's got videos of himself, so you take a plane and you do this parabolic sort of flight shape, and then you get weightlessness for a certain amount of time, sort of a small amount of time. So he's got data from that, and I was pretty jealous because I didn't get to go on those flights. Although probably I would have been sick. So, maybe that's better. Then I went to the University of Toronto, which unsurprisingly is in Toronto, and I started to work on what we call digital microfluidics, right? Making use of something we call electrowetting on dielectric. Now, these devices look something like this. It's this checkerboard of electrodes with fluid that's sandwiched between 2 plates, right? So the little droplets are kind of like the white part of an Oreo cookie. We make both plates hydrophobic. And then the cool thing is, when we apply an electric field, we can move these droplets around, right? So the fluid mechanics here is interesting. So this, here we can sort of create this droplet, split it off, and move it back and forth, right? So here, just in this video, each check on the checkerboard is on the order of maybe 1.5 millimeters by 1.5 millimeters. And the separation between those 2 plates is about 100 micrometers. So maybe about as thick as a human hair, or like a piece of Scotch tape. Now, as you continue on in mechanical engineering, you'll learn about vibrations, right? So vibrations are something like, if you think about a tuning fork or maybe a diving board, right? And when you dive off a diving board, it kind of oscillates back and forth, right? You can model that like a spring, right? Hooke's law, right? So force equals displacement times the spring constant, right? and damping, which is kind of like friction, right? If you think about a damper on a door, right? So if you pull a door open, but if it's got a damper on it, it closes kind of slowly, right? It's got maybe some oil in there and a piston, so that makes it go down slowly. So if you understand sort of the spring in your system and the damping in your system, then you know something a little bit about the dynamics. Now here, these droplets, when we uncover them, you know, that interface of the droplets a little bit like the skin of a water balloon, right? It's got some elasticity to it, kind of like a spring, and then there's some friction inside the fluid, right? And that's the damping, right? But here, these are not very damped, these systems. So if you know how to apply the electric field, then you can get these droplets first to spread out, but then if you remove the voltage at just the right time, then you can get these droplets to jump up off the surface, which we think is kind of cool and maybe has some utility too. So we talked about, I don't know if this has ever happened to you, but sometimes if you have like a window air conditioner, or even in my central air system, we had to get it replaced like right at the beginning of the pandemic, and because it was low coolant, so it would ice up all the time, right? Now, part of the thing that happens when it ices up is it gets cold and there's maybe condensation on there and it freezes. Right? But if you could eject droplets from that condenser, then maybe you could prevent that ice buildup, right? And the videos are cool, right? Here we slowed it down so it looks a little bit like, you know, a bowl of Jello or a water balloon or something, right? Now, usually to make these kind of things, you got to go into the clean room. I don't know if you've seen the clean room in Building 17. You walk by, there's like, you know, yellow panes of glass there, and people are all in the ninja suits in there. They're making like microchips and stuff, right? But you need to do a lot of training to get in there. It's a pretty high technology chemistry lab. So, you know, instead, we're trying to make these kind of devices outside of the clean room using an inkjet printer that we've modified a little bit to print some conductive ink. We can get relatively small features. So here we can print out the types of devices that we're using. But, you know, if an undergraduate came in and was trying to do some work with us, they wouldn't have to spend 6 months getting trained up in the clean room, right? So the reason that we're doing this, my brother's a biochemist, and I actually spent a summer in a biochemistry lab, you know, pipetting a bunch of stuff all over the place. And it's like, you know, doing some biological stuff and the experiment fails, so you got to do it again. So we're trying to automate all that stuff. So it's, you know, there's less labor costs. Maybe you can do things more quickly. So we were working with a company in the UK, and they were interested in fusing pieces of DNA together. So you could go from small DNA pieces to large DNA pieces in a repeatable way, right? So on these devices, we were mixing together two small pieces of DNA. Maybe because I'm a mechanical engineer, I think of these like Lego bricks, right? We did some chemistry on the chip, and we made a larger piece of DNA. So we're trying to give biochemists, so my brother's a biochemist at the University of Binghamton, we're trying to give people like him tools so that they can do some of the bench work faster, so that they can, you know, spend more time doing science, right? So we're trying to automate things. So different applications of the work that I do. So we're looking at, you know, lab on a chip stuff. So trying to take like a lab like my brother's and shrink it down on a microchip. You know, we're interested in looking at droplets and how they dry and what's in the droplets and where they go, right? So we think that that's got some interesting applications in things like printing and flexible electronics, in blood diagnostics. So you can check out things like lipid analysis by drying out droplets of blood and looking at the patterns that they form. You know, it's a little bit different, but I don't know if you ever saw the TV show Dexter, right? But it's kind of a similar thing based on, you know, blood spatter and how that stuff dries. You can tell a little bit about what happened, right? We've also done some work in the past looking at lubrication and trying to reduce friction. So we're still interested in that area, although we don't actively have a project there, right? This is a shameless plug for the lab. I've had the opportunity to work with a lot of great students at RIT. So if you're interested in any of the work that we do, just let me know. Right, so like every class, the first lecture here, we're going to talk about the syllabus, basically how the course breaks down. So the syllabus is posted on my courses. I I think just generally, like I said, I don't really want to read the textbook to you, right? And actually, you're welcome to get any version of the textbook we're using. It's called Fundamentals of Engineering Thermodynamics. Morin and Shapiro are the first two authors, but there's also Bouthier and Bailey. You can, if you get the book, try to get a really old version of the book. Like I have the 4th edition from when I was an undergraduate. And it's basically the same, especially the material. It's got a lot of good examples in there, but we're going to post all the questions that are related to the homework. So if you're somebody who's really just using textbooks so you can get the homework problems, we're going to post all that for you. And again, I post all my notes, and there's lectures of all the, or videos of all the lectures. So you're welcome to use that too if you feel like you don't need the textbook. Now, again, I would say that the textbook does have a lot of good examples in it. So if you can get your hands on a copy of it, I think that's good. I think it's useful, but I wouldn't pay full price if it were me. So we're going to try to, to get you to have a deep understanding by doing problems. And I'm going to hope to do a bunch of problems in class. This will be a little different than normal delivery, right? Because usually this is a Monday, Wednesday, Friday, for 1 hour kind of class. And now it's a Tuesday, Thursday for 3 hours at a time. So basically we're doing a week. Every day we have a class, right? But we're going to try to get through a bunch of problems. So hopefully we, we get through a lot of problems, and that gives you some understanding of how to do the problems. But it is going to be like drinking from the fire hose. So you're going to have to try to keep pace, right? It's going to be real easy to fall behind, I think, because we're going to go through things so rapidly. We're going to have sort of the typical grade breakdown that we usually have in sort of a core engineering class, where nominally each of the exams will be worth 25%, the midterms. The final will be worth 30%, and then we'll have 10% for homework and quizzes. Now, I'm a lot more interested in what you know at the end of the class versus what you know at the two sort of checkpoints along the way. So I'm also going to run everybody's grade. You don't have to do your own calculations and tell me what you want to do, but I'll run everybody's grade 3 different ways. Taking this sort of general breakdown here that we see, but then also if let's say you have a bad day for midterm 1, right? But then you show that you know how to do that same material on the final, then your final can overwrite one of the midterms, right? So nominally it's this breakdown here, but your final can be worth 55% if you score better on the final than on either one of the midterms, right? And like I said, I'll calculate that for everyone. There's nothing special that you have to do to check it out. This is just at the back of the syllabus. Sometimes I think it's nice to have a look at what the calendar is, right? So we got 6 weeks. Again, we're sprinting through the class here. So we'll meet Tuesdays and Thursdays in this time slot. And then finals are here the 5th, 8th, and 9th in August. I'm going to suggest, and I don't think I'll get much pushback from the class, that we write the exam on either the 8th or the 9th, so you have that weekend to prepare. But as we get closer, we'll finalize a date. And again, because there's so few of us, if we need to have some kind of, if you're not available whenever we have, set exams, then we can sort of have an alternate exam for people. So it'll be a different test, but it'll be at a different time if you need it, right? But we'll try to get everybody so that we're writing kind of in the same evenings. So this is what we're going to do for a typical week, right? So if you look at the syllabus, and I think I have a picture of it coming up, for each lecture, there are the topics and then the problems that are associated with those topics. I have an image of that in just a second. So like today in the thesis, this is lecture 1A, right? So related to lecture 1A, we'll have homework 1A, which is due on Friday, right? Beginning this Friday. And then we'll have a quiz related to lecture 1A that's due on Saturday. So both of the due dates are by midnight, right? So it's kind of like Cinderella, right? So you got to be in there before 23:59 or 11:59 p.m. Lecture B will be on Thursday. The homework from lecture B will be due on the following Monday. And the quiz for lecture B will be due by the following Tuesday. Now again, because there's not many of us, right? If you do ever have some issues with timing, you can just let me know, and probably we can work something out. But we're going to try really hard to stick to this schedule, because if we start to have things slide, it's going to pile up really quickly, right? Because we're going to have so much to do every week, right? So for your quiz grade, we'll take the average of all the quizzes that are on my courses, and for the homework grade, we'll take the average of all the problem sets. So it's not super difficult to calculate your grade, but it all come out in my courses too. So for a typical homework, right, it'll look something like this, right? You'll have some amount of problems that are assigned. What I'll do every time is I'll randomly select one of the problems that I'll grade a little bit more in depth. That'll be worth 7 of the 10 points. Right? I'm not exactly trying to grade, did you get the right answer? Because one of the things we're really going to try to hammer home is this kind of engineering ethos that the process is the most important thing, right? Now in engineering, results matter, right? Because if it's cliche, right? But if you build a bridge and it falls down, that's not good, right? People die. So you don't want to fail, right? But the best way to get good results is to consistently follow a good process. Right? So most of the points will be for the process, right? So did you attempt the problem? Are you following the correct format? Right? If you're unsure of our problem format, look at lecture 3, the notes for that. It goes over what the what the problem format is. Are you following the correct solution method? Right? And then basically I'm going to see, did you attempt all the other problems in the problem set? Right? And if you attempted them, I'm not going to look how deeply you did it. I'm just going to give you 3 points. Right? So if you're trying to find out the homework problems that are due, this is what the syllabus looks like if you haven't had a chance to look at it. Right, so lecture 1A, that's today. We're going to cover these lectures, 4, 5, and 6. If you look at the notes or my lecture videos, those are the numbers for the lectures that they correspond to. And then over here, these are the homework problems. Right, 2.23, 2.46, 2.50, and 3.7. Right? So these are the homework problems for homework 1A, right? And then these next ones are the homework for 1B. Right? Now, if you're trying to find what those homework problems are, if you have the most recent version of the textbook, that's fine. You can just look them up there. But if you don't, you can go on to my courses, click on content. If you click on homework problems, and then you click over here on Thermo all homework problems for 22 or 2218, right? So that's this summer session. This is going to be all of the homework questions that are assigned, right? So you can see what all of the problems are there. Now, this next part's a bit of a double-edged sword, right? It's a blessing and a curse because I'm posting all of the solutions right now, right? So if you want to find all the solutions, right, you just click on homework solutions, you click on here, and you'll get all of the solutions, right? Now, don't just look at the solutions and write them down, right? Because first, I think that the solutions that come from the people that make the textbook, I don't always like the method, and certainly it doesn't always follow the same method that we talk about in class, right? So again, the process is as important as the results, right? But second, you're not going to learn anything, right? And in the exam, you're not going to have a solution for the exam problem, right? So my advice to you is to look at the problem, try to do the problem on your own, and then go back and look at the solution and see if you got it right. See if you didn't get it right, what could you do differently, right? And try to keep a log of yourself, like to reflect and say like, I kind of had problems calculating work, right? So how do I calculate work? Right? And then, if you keep notes like that to yourself, then when you go back and study for the exam, you say, I was really good at finding the change in specific internal energy, but I had some problems trying to find the work. So that's the thing that I want to focus on, right? So keep notes and try to, be honest with yourself. Sometimes ruthlessly honest with yourself to say like, these are the things that I want to look for on the exam. Office hours, I think office hours are important. I like to think that it's beneficial. So I'm going to schedule some Zoom office hours based on feedback from you to see when people are available. So please come, right? We can go through problems. Even if you want to sit down and go through the homework problems, we can do that, right? And just go over the solutions. How would I go through all these homework problems, right? And if that helps you learn, that's great, right? So there is a when to meet link in the announcements on the My Courses page. You don't have to try to copy this down, right? But if you click on that, 3 out of the 5 of us have submitted their availability. It looks like any time in the afternoon is good for the people who have submitted. But if you fill this out, then I'll be able to find office hours that work for you. Right? So I have videos of all the lecture content for the class, both in 1-hour lecture format. I'll try to post these 3-hour lectures. We'll see how the computer deals with all the data that we're recording here. But if you want to look at videos, so you go to My Courses, there's a couple of different things here. Sure, there's pre-recorded lectures and starter sheets. So this is the full-length lectures. So basically 1-hour lectures that I would normally give in a standard semester. The starter sheets, those are the problems we're going to do in class, right? So those would be like the Word document that I hand out to people. And then there's these thermo shorts. So what I try to do in the thermo shorts is take those 1-hour lectures and boil them down to 5, maybe 10 minutes. What are the big ideas that we covered in that lecture? So I think that's probably, I've had people suggest to me that that's kind of useful to look at sort of before lectures, or maybe, as they're studying, to kind of see like, what's the big picture? What am I supposed to get from this lecture? So you can click on those if you like to. Both the 1-hour lectures and these thermal shorts lectures are fully captioned by humans. So we, when we shut down for the pandemic and we were giving this all virtually, we paid some TAs to go through and transcribe all of the videos. So those should all be fully captioned. Right, so these are kind of 5 to 10 minute recap videos. You see here, maybe it's not on this list, but my notes are also posted, which my notes are basically just the PDFs of the PowerPoints that I go through. Right, so all that stuff is available to you now. It's not like it's timed or anything. You can check it out whenever you like. Right, so if you click on this, right, so this one was lecture 4, so the lecture we're kind of going through now, right, and it's like 5.5 minutes, right, so you can check that. That's the big idea. How do we calculate work? If you want the starter sheets, right, then you would click on this pre-recorded lectures part, right? You can see here, this is a link to the full-length version of this lecture, and then a link to the PDF of the example problem we're going to do in class that corresponds to lecture 4. Now, it is a little weird in this particular session because, the lectures don't exactly fully match up, right? Because our first lecture is lectures 4, 5, and 6. But if you look on the syllabus, the lecture number that corresponds to the video and the notes, there's sort of the Rosetta Stone there. So you can see, our lecture 1A is lecture 4, 5, and 6. Right, so this is what the starter sheet looks like for the second problem that we'll do in today's kind of long lecture. So now we can start talking about thermodynamics. Right, so I think that this is, and again, I'm not unbiased, but I think this is the coolest class that you're going to take in mechanical engineering. At least the first, I think, really, really cool class. The first class where I think we start to get to see what it's like to be an engineer. To me, in engineering, we would like to be able to design things or improve things, even though we have an imperfect understanding of the universe. Right? So what happens a lot of times, particularly when you're talking about what we call the thermal fluid sciences. So that's thermodynamics, that's fluid mechanics, that's heat transfer. So all of these things we're talking basically about energy transfer, which is sort of how the universe works, right? The problem is, the good news here is that we've got great equations that we think work really, really good, right? The bad news is that for most practical problems, the problems are not well posed. What that means is that even though we've got great equations, we have more unknowns than we have equations, right? So we don't have a system of equations that we can just solve by brute force. So what you need to do is use your understanding of the physics to start to think about which terms in the equations, what do they mean, and how are you going to prioritize different terms? What terms are the most important, right? And that gives you what we call a model of the universe, right? So an estimation of how the universe works, right? So when we start talking about thermodynamics, we're interested in energy transfer, right? So we're going to look at the universe, right? The universe is this big blue blob that's on the screen, right? And we're going to break the universe into two parts. The first part will be our system. That's the part of the universe that we're most interested in, right? And then there's the surroundings, which is like the rest of the universe, right? The thing that the system is communicating with, and the way that it communicates is that it can transfer things like energy and mass between the system and the surroundings. Now, when we look at these problems, there are a series of really fundamental questions that we have to ask ourselves, right? Now, the first one is what's inside of our system. So you could imagine that if I have 1 kilogram of copper and I heat it up from, say, 20 degrees Celsius to 110 degrees Celsius, it's going to act differently than if I have 1 kilogram of water that I heat up between those same two temperatures, right? So what's in the system really matters, right? The next question that I might want to ask myself, or another question that I might want to ask myself is the system open or closed? Now, if you did look at the notes for the first 3 lectures, you might know what those words mean, but if you didn't, an open system is a system where mass can pass between the system and the surroundings, right? So let's say that I'm making mac and cheese, right? So I'm boiling my noodles, right? But I have the lid off the pot, right? So now as I'm boiling water, it turns into steam, and that steam can escape, right? So that's an open system. But a closed system might be I'm boiling those same noodles, but now I'm doing it in a pressure cooker, right? And our pressure cooker is kind of open too, right? But we'll pretend that it's fully closed, right? And then what happens is as I boil the water, I trap steam inside the vessel, right? Which increases the pressure, which means that I have a higher boiling temperature, right? But we'll see how that works, right? So I got to ask myself, can mass leave or enter my system, right? Then I want to ask myself at the initial time, the time when I start my experiment or when I start looking at my system, how much energy do I have in my system at my initial time, right? So if I have water that's at 20 degrees, it has a certain amount of energy that's bound up in it, right? But then if I wait a certain amount of time, tau, then at that later time, it's going to have a different amount of energy that's stored in the water, right? So if I take that water up from maybe 4 degrees, it comes out of my tap, 4 degrees Celsius, and maybe I increase that temperature to 80 degrees, so it's not boiling yet, right? But it has a different amount of energy in it, right? Because all that energy that I put in, waiting and waiting for that pot to heat up, gets stored in the water as temperature, right? Now, this is what, this is kind of the nuts and bolts of thermodynamics. So in thermodynamics, the thing that we're interested in is, the things that we're interested in normally are heat transfer and work, right? So this isn't true for every kind of thermodynamics. My brother, like I said, he's a biochemist. He took a class called physical chemistry. Physical chemistry is like the thermodynamics of chemical reactions. Everybody hates that class, right? There's a little bit like, when I first started teaching, we get advisees, right? And I was meeting with the head advisor at the time, and they got all the advisees that were advising first year students who came together in a room, because we used to come together in rooms. And she would ask us, Hillary went through and she asked all the professors, try to humanize us, which is not always an easy task, right? And they said, well, what was the class that you disliked the most when you were an undergraduate? For me, it was probably something like material science, right? But for maybe half the professors in the room, they were, thermodynamics, right? So I'm like, but I love thermo, right? I think it's kind of this bimodal thing where some people really love this class, and some people are just trying to get through it because you have to, because it's required, right? because there's lots of ideas that are different in this class. I think mechanical engineers, a lot of times we go into mechanical engineering because we like problems where we can picture the answer, right? So if I take a pendulum and I pull it back and I let it go, I can imagine that that pendulum is going to swing back and forth, but the amplitude is going to get smaller and eventually it's going to stop, right? Or if I, it's like the cannonball or roller coaster problems, right? I can imagine what's going to happen in those problems because I have some engineering intuition. But in this class, we start to talk about like how much energy is in steam when it's at 1 atmosphere and 100 degrees Celsius, or when it's at maybe 10 atmospheres and I don't know, like 300 degrees Celsius, right? So it's going to be a little bit, we're going to have to expand our minds a little bit. Now, it's a difficult class, and we're going to go through it quickly, but I hope if we can stay on pace, particularly if you're doing things like coming to office hours or asking questions in lectures, we're going to be able to get through it, right? But these are the questions generally we're going to ask on almost all the problems we're going to look at in the class, right? Now, it makes it look easy on this slide, right? But it gets hard, right? It gets to be kind of complicated because it's a bit of a choose your own adventure. And depending on the case that you're talking about, you have different strategies for doing different things. Now, in this class, this first lecture, we're going to start to talk about how do we find out the work, right? So thermodynamics, the name kind of comes from, Greek. Thermo is like heat, right? Dynamics is like work. So the name sort of comes from, the Industrial Revolution and the generation of the steam engine, right? Because that's what the steam engine does, is that you burn coal to make heat. You make that heat to boil water, right? And that steam expands over some kind of a system, which makes the wheels turn. So you're turning heat energy into mechanical work, right? That's that energy transaction that you're doing, right? So today we're going to start to talk about how do we calculate work, right? And what's power, right? So I don't know, somewhere when someone defined this class at RIT, they talked about these core principles of engineering, and they called this one core principle 5. So that survived on my slide here, right? But it's really conservation of energy, right? There's some words here which you can read if you want, but I'm going to suggest to you not to think about this in terms of the verbal definition. Basically what this says is that energy is conserved. Particularly in this class, we're not going to talk about nuclear reactions where we can change mass into energy directly. So we're going to be talking about other types of energy transactions, right? So in the simplest form of the first law of engineering, of the first law of thermodynamics, which is conservation of energy, instead of writing it in words, we can write it in math, right? So what this says is E2 minus E1. Now, E is the total energy contained within our system. E2, so the subscript here is related to a moment in time. So the total energy in our system at end time, time 2, minus the total energy at the initial time, time 1. Right? So this is going to be all the different kinds of energy that are associated in our system. Right? And our subscripts denote moments in time. Q, I don't know why, but Q is the letter that we use for heat transfer. So we're going to say that change in total energy in the system for the types of energy transactions we look at in mechanical engineering typically comes from heat transfer into the system. So doing things like putting that pot of mac and cheese on the stove. So we're putting heat into it. Right? So this is heat transfer into the system. Now our subscript is from 1 to 2. So as we're moving from state 1 to state 2, so the energies are about moments in time, and the heat transfer in the work are about the process, how we walk from that first moment in time to the second moment in time. Minus W, this one makes a little bit more sense. W is work. So this is the net work done by the system on the surroundings. So again, the subscript here from 1 to 2 means we're moving in time from the earlier time to the later time. right? So this says the same thing as those words, that energy is conserved. And the assumptions that we make in this class are that the change in the total energy in the system are the result of heat transfer into the system and work coming out of the system. Right? Now, I like describing things in math, right? But I like pictures even better. I think that for most problems you're ever going to do in any engineering course, you should draw pictures. Things like free body diagrams, or we'll draw different kinds of diagrams in this class, right? But I might want to draw my system, right? And it has some amount of energy at the initial time, right? And then what happens if we add heat, right? If we add heat to the system, right? What happens is, and you know this, right? If you put a pot of water that's at 4 degrees Celsius, you put it on the stove, you're adding heat, the temperature goes up, right? Assuming you keep the pressure constant, right? Now, as the temperature goes up, you store more energy in the system, right? So as you put heat in, the energy in the system would go up, right? This one's a little trickier, right? Because this is now work coming out of the system, right? I don't recommend that you do this, right? But if you know what a potato gun is, right? You get something like a PVC pipe, you stuff a potato in one end, right? And you do something inside the chamber that increases the pressure dramatically, right? In a small amount of time. What happens is eventually, there's some static friction of the potato in the barrel, right? And then eventually you overcome that static friction and the potato shoots out, right? So that's the pressure in the system is pushing that potato. It's doing work on the potato. So energy starts to leave the system because that gas is expanding. It's pushing outward, right? So as work is leaving the system, the energy in the system goes down, right? So work is done by the system on the surroundings. If the gas is or if your system is expanding, the volume is getting bigger, then the system is doing work on the surroundings. But conversely, if you take a piston cylinder assembly and you push it in, right, now you're putting work into the system and you're compressing that gas, so the energy goes up, right? And depending on the heat and the work that is happening, you'll get some amount of energy stored in your system at time 2, right? So this is what conservation of energy is in relation to this thermodynamics class. That the change in the energy in the system happens because of heat transfer going in and work coming out. Right? Now, we've got some sign conventions, and they come both from the math and from sort of this historical artifact of the steam engine. Right? So I think this picture is cool, so I put it in my presentation. Right? Now what happens here is that we burn coal to make heat, and we use that heat to boil water, right? So that's heat going in. So we have this sign convention that heat goes in. When heat goes into the system, that's a positive value. Q is positive if heat is going in, right? But in this steam locomotive, we're generating work, right? So when work goes out, it's positive too, right? So it's a little bit weird because when heat goes in, it's positive, right? But when work goes in, it's negative, right? We have a mnemonic that we talk about is HIP to win. HIP is heat in is positive. Win is work in is negative, right? Right, so we have this conservation of energy, right? All the energy stored in the system at time 2 minus at time 1 will give us the change in energy in the system. Right, now, you probably took some kind of high school physics class or maybe University Physics 1. I'm sure they talk about this too. Right, now, when I took those classes, mostly when they talked about energy, they talked about gravitational potential energy. Right, so like, when I push my daughters on the swing, right, they're trading off gravitational potential energy for kinetic energy. Right, so I'm kind of used to those two kinds of energy, right? And maybe I know something about spring energy. So I don't know if you ever play video games with bow and arrows. They always animate this wrong, right? Because they use it like a sling bow. They make it like the string is stretching. But what actually happens in a bow and arrow is when you draw back, right? You bend the limbs, and the limbs are like a spring. So you're storing potential energy in the spring, and then when you release, right? Then what happens is that potential energy, the spring energy that's stored in the limbs, gets transferred to the arrow as kinetic energy. Right? This is a picture of me. This was just a crazy shot, totally by accident, right? I was shooting for the center, which I hit, right? But I shoot a recurve like in this picture, and I was shooting with some guys that were shooting compound bows. So I had we were using carbon fiber arrows, so they're hollow, right? I'm not sure. I think on Mythbusters, they say you can't really do this, right? But I think they're talking about solid arrows that are coming right on each other. But because I had a smaller hollow arrow and hit right at the back of a larger diameter hollow arrow, I stuck it right in there, right? So it's unfortunate because I wrecked the guy's arrow, and arrows are not cheap, right? But it was pretty cool, right? One of the kinds of energy that's going to be really important in this class, but I never heard about in like high school physics or University Physics 1, right, is this idea of internal energy, right? I bet you, because you live on Earth, looking at this picture, you can tell me what part of these pins has more energy, right? Because what happens is as we increase the temperature of something, the amount of energy that's stored in that mass is different, right? It's stored as this change in temperature. Similarly, with a fluid, as we change the pressure, then I'm also changing the energy, right? So this internal energy is something about the temperature and the pressure of whatever kind of mass that I'm looking at inside my system. Remember when we said we're dividing the universe into the system and the surroundings, one of the questions we had was, well, what's in the system? Right? Because that matters. It's easier to increase the temperature. It takes less energy to increase the temperature of copper than it does to increase the temperature of liquid water. Right? So really this term E in our equation, the total energy in the system at a particular time, is the sum of all the different energies that are associated with the system. Right? So kinetic energy and potential energy and spring energy, we kind of know about those things already. Right? But then there's this other thing, U, right? So this is the internal energy, and that's got something to do with the temperature and the pressure. Right? So this total energy is made up of all the different kinds of energy in the system, right? Kinetic energy, potential energy, spring energy, and internal energy. Internal energy is going to be the focus of this class. We talk a little bit about kinetic and potential energies. We rarely talk about spring energies. If you think about like an internal combustion engine, if your cylinder, right, in your piston cylinder assembly, if it's deforming, if you're storing potential energy because of the deformation of your engine block, that's not good. You want that to be rigid. Right, so we try not to think about things like, we're trying to design systems so that spring energy is not that important, right? So it's this internal energy that we're really interested in, right? So the change in this internal energy in our equation could really be written out as the change in the kinetic energy, plus the change in the potential energy, plus the change in the spring energy, plus the change in the internal energy, right? So my first law of thermodynamics, my equation for conservation of energy, is really all of these different energy changes are equal to the amount of heat that goes in minus the work that goes out. That kind of makes sense? So you kind of know this already, right? Because you've done things like cannonball or roller coaster type questions It's just in a class like engineering mechanics or university physics or high school physics, we just assumed that the change in the internal energy was zero, right? But nobody ever really told us that, right? We assumed that heat transfer probably didn't matter, right? And maybe we even neglected the work that was going on. So, when you talk about pushing my daughter on a swing, normally we talk about, we're just exchanging potential energy for kinetic energy. Right? So we were making a bunch of assumptions that we didn't even really know. And that's why when we look at our format for the homework problems, when you're developing a model, an engineering model of the universe, when you're turning the universe into a cartoon, right, you have to keep track of the assumptions that you're making. Because then when you run the experiment, if your predicted results don't really agree with reality, you go back and you look at your assumptions. What are the terms that I crossed out that might actually be important, right? So in thermodynamics, because we're really interested in something like a steam engine, where we're adding heat to boil water so that we can get work, right? Those terms that we often crossed out in something like engineering mechanics actually are really important to us, right? So we will always start. When we talk about closed systems, my advice to you is always write down this equation. The change in the kinetic energy plus the change in potential energy plus the change in spring energy plus the change in internal energy is equal to heat transfer minus work. Because if you start with this equation, you have to show me your assumptions, because you'll start to cross off a bunch of terms, right? And when I look at exams, one of the main reasons, sort of easy points that people miss is they start from a more simplified version of the equation without telling me how they got there. And I can't just assume that you know what you're doing. You have to, the purpose of an exam is to give you an opportunity to demonstrate your understanding of the material, right? So you have to explicitly show me what your assumptions are, right? And we'll get some practice doing that as we do some problems. Now, I talked about this lecture as being about work and power, right? So if you think about an internal combustion engine, they don't rate it by the work that it does, at least not directly, right? They'll talk about how much horsepower your engine has, right? Now, what is power, right? So power is the work divided by some time interval, right? So it's the first derivative of work with respect to time, right? Now, we're going to use this kind of nomenclature where if we have a variable and we put a dot over it, that's shorthand to us telling us we're taking the first derivative with respect to time, right? So W is work, but W dot is power, right? So that's, so anytime we have a dot, we're talking about the rate of change with respect to time, right? Now, this is a bigger deal for the second third of the class. The class is basically broken down into three parts. The part before the first exam, we're going to look at closed systems, systems where mass doesn't enter or leave our system. The second third of the class, we're going to look at open systems, things like pumps or wind turbines, right? Or steam turbines, right? Where mass is coming in and going out. Right? And in that second part, we start to worry more about power, right? And then in the third section of the class, we're going to start to look at, okay, well, how do we chain together each one of these processes as we move from one state to another into usable things like heat engines? So how do I describe an automobile engine, right? How do I describe a nuclear power plant or a gas-fired power plant or an air conditioner? Right? So we start to look at these practical machines that we're interested in when we talk about mechanical engineering. Right? So power is work divided by some delta T, but then you take the limit as delta T goes to 0 and you get the first derivative, right? Right? This is pretty simplistic here, right? Right? So if you produce 1 joule in 2 seconds, right? You would take 1 joule divided by 2 seconds and you'd get 0.5. But this is the other thing that I'm really, really going to hammer home on, all the homework that we do and in the examples that we work on is you have to carry your units inside your math, right? Because now we can see that 1 joule per second is equal to 1 watt, right? But if this was 1 kilojoule in 2 seconds, right, then we would get 0.5 kilowatts, and you get a very different answer, even though numerically it's 0.5 both times, right? And the thing that you're really going to hate is that we're going to do problems in the metric system, but also in the imperial system or the US customary system. So the imperial system is nice because it's base 10. So you divide by things like 1,000. That doesn't happen in the imperial system, right? So I guess we got elections coming up, so you can write your Congress people and get them to change everything to the metric system, because you're probably not going to like the imperial system after this class, right? Because there's tons of unit conversion that happens in this class. And, you know, we're going to talk about things like tons of ice for an air conditioner, which doesn't make sense because it's a heat transfer. It's a unit of heat transfer, right? And it sounds like it should be mass, right? Right. But you also deal with like pounds mass and pounds force are 2 different units, right? So it deals with lots of problems, right? But we're trying to talk about work, right? So here you can imagine that this is something like a potato gun, right? So we have a pin that's holding this piston in place, right? Maybe that's the potato in our system, right? And we have some fluid in here. Maybe it's air, right? And it's at some pressure, right? But if that pressure is high enough that it would move this piston, right? Then when we remove the pin and the piston is able to move freely, this gas is going to expand because it's a high pressure. It's going to shoot that piston out. It's going to do work on the system, right? So how do we calculate the work in this problem when we pull the pin, right? Because remember, the change in energy stored in that gas, which is stored in this case mostly as a function of the pressure, right? That's a form of potential energy. Now, as we pull that pin, that pressure is going to decrease, but the piston is going to move, right? So here, we know that the force on the piston face is equal to the pressure times the area, right? Now, if we were talking about the metric system, pressure is in pascals or newtons per meter squared. Area is in meters squared, right? So we'd get newtons if we do that out. Pressure in the imperial system is often pounds per square inch. Area might be in inches squared, so we get pounds force, right? So again, you get force in both of these cases. It's always nice to check out these kind of equations. They don't prove that the equation is right, but if I get the unit that I'm looking for, if I'm saying that it's equal to force, and I get a unit of force, then I can't prove that my equation is wrong, right? And that's pretty good. That improves my confidence, right? But if I get the wrong unit, I know my equation is wrong, right? I'm going to make the argument here that work is the integral of force over distance, right? Which makes sense, right? Force times distance is work, right? Is energy, right? And it's joules in the metric system, right? Newtons times meters, or it's inch pounds, pounds force times inches, right? But I'm not exactly going to write it out this way because I want this as a function of pressure, because it's the pressure in my system that's going to change as that piston starts to move, right? So my force is the pressure times the area, right? So the force, if I put pressure times area in here, then I'll get pressure times area times some small incremental distance, right? Which is pressure times some incremental volume, right? So again, I'm not doing a proof here. I'm not showing you that this is true, but I kind of want to check it out, make sure that it makes sense, right? So if I take a pressure in metric, that's going to be pascals, newtons per meter squared. I'm going to multiply that by cubic meters, and I get Newton meters, right? That's energy, right? Force times distance, right? That makes sense, right? Similarly, if I take PSI, pounds per square inch, times cubic inches, then I get inch pounds, right? Which is also force times distance, right? So I didn't prove to you that the equation is correct, but hopefully you've got some confidence in me, right? It's also in the textbook, right? If you bought it. But if you didn't, you're going to have to trust me. right? This relationship for us is very important, right? This is how in closed systems we're going to determine the work in our process as we move from time 1 to time 2. The work is going to be the integral of P dV, right? Now, this only really works. We can, well, maybe not only, but this works a lot better if we know the pressure as a function of volume, right? Because if we know the pressure as a function of volume, then I can substitute that into my integral. I can do a little bit of calculus, and I can find what my work is going to be, right? So we're going to deal mostly with processes that we call polytropic processes, right? So this is maybe one of the reasons people don't like thermodynamics is there's lots of these kind of engineering decoder ring type words, right? So you need to know, it's funny, right? So we call it the nomenclature, which is itself one of these engineering decoding ring type words. That's like the vocabulary associated with a particular subject, right? So if we have a polytropic process, that means that pressure times volume to some exponent is equal to a constant. And depending on what we know about the process, we can have different values of n, right? Like if I had a pressure that was constant, n is just 0, right? Because then v to the power of 0 is 1, and the pressure is constant, right? We'll have some more complicated integrals than that, but that's kind of the simplest version of this, right? So I think we're through about an hour. We can take a little bit of a break from thermodynamics. I'll give you maybe 5 minutes or so. If you need to run to the bathroom or grab a drink of water, we'll do that, and we will start up again in about 5 minutes. Sound good? Cool. Does anybody have questions so far? You're welcome to type those in the chat. While I'm talking too, I'll always try to keep an eye there. Thanks, everybody. All right. Welcome back, everybody. I don't know how much just a couple minutes makes a big difference, but I don't know. I think it's hard to concentrate for too long doing this, and even hours at a time is like 1 hour at a time is probably too much. So I appreciate you sticking with it, right? So in the first hour, I think the big take home is that we can draw the universe like this, right? So we're going to separate it into the surroundings and the system. The system is the part of the universe we're most interested in. We're interested in the amount of energy stored in the system at some initial time, right? Now, typically we'll be thinking about things like what are the pressures and the temperatures, right? And then at some later time, the pressure and the temperature are going to change, which means that the amount of energy that we've stored in the system is different, right? Now, we're going to argue that most of that energy change, if not all of that energy change, for the types of processes we're interested in this class, comes because of heat transfer and or work, right? Now, to answer or to do a type of problem, everything basically before the first midterm is this picture, right? It's a closed system, right? So what's in the system? Is it open or closed? And before the first midterm, it's nice because the answer is always going to be closed. What's in the system typically for us is either water or something like it, something that boils and condenses, or some kind of an ideal gas. We rarely deal with solids in this class, almost never, right? So when we have this question, right, because we've assumed that it's a closed system, then we can write down the version of the first law that we know, right, that we talked about in the last hour, that the change in the energy stored in the system is equal to Q minus W. We'll see as mass starts to come in and out of the system that the equation gets more complicated. But we don't have to worry about that until after the first exam, right? So for now, this is where we're at, right? And then we want to know what happens to the system, right? And so far, we've talked a little bit about work, right? So we're going to do some examples in the next hour that sort of talk about or demonstrate how we're going to calculate work. Right? So we know that delta E is the change in the energy stored in the system. Right? That Q is the amount of heat that goes in to the system. Heat in is positive. Right? So we talked about this idea of hip to win. Heat in is positive. Work in is negative. Right? So the net work done by the system on the surroundings, work in is negative. So the way that we can tell is when work goes into a system, it compresses. The volume gets smaller, right? And we'll see this from the calculus because the work is the integral of PdV. Because pressure is always positive, because we're going to talk about absolute pressure. So we're going to compare the pressure to the pressure in space where there's nothing, right? So pressure is always positive. If the volume gets smaller, then work is negative. Work in is negative. But we'll see what happens is negative work. That means that this would be minus some negative number. So the energy goes up because we're storing energy in the system, right? But if it expands like in the potato gun, right, then the volume gets bigger, work becomes positive, which reduces the energy because now you have a negative times a positive, so it's negative, right? And E2 goes down. So I'll talk about this more as we start to prep for the first exam, but this is thermodynamics class. The first law of thermodynamics is the most important equation that we ever use. And you're going to use the first law of thermodynamics basically in every problem that we do. So if you ever get lost on an exam, write down the first law, right? And write it down in the longest form that you can. So right now that's delta. It's really not even just delta E is equal to Q minus W. It's the change in kinetic energy plus the change in potential energy plus the change in spring energy plus the change in internal energy is equal to Q minus W. And then you can start to make assumptions. Oh, what do I think is important, right? You can start to cross stuff off. And we'll start to see how to use that. We haven't really done that yet, but we'll start to see how to do that, right? Throughout the class, we're going to use different forms of the first law of thermodynamics. But right now, and up until the first midterm, all we know is the closed version of the first law. Delta E is equal to Q minus W, right? No matter what version of this equation that we're using, it's always just conservation of energy, right? That the change in energy of the system is equal to the heat that goes in minus the heat that goes out. It just gets more complicated when mass is coming in and out too, right? And in the most basic case, right, again, I like not the words, right, but the equation and the picture, right? You're going to get tired of seeing this picture up until the first midterm because I'm going to show it so often and hopefully that kind of burns it into your brain, right? We've been talking about how to calculate work, right? Because ultimately what we're going to do, sort of the flow chart, which I'll present at some point, right, is you won't really learn how to calculate heat transfer directly until you take heat transfer in like a year and a half, right? So what we're going to do for closed first law problems almost always is we're going to write down this equation. We're going to make some assumptions. We're going to calculate work as the integral of PdV. And then we're going to find the change in the internal energy. We won't talk about how to, well, I guess we might start to talk about how we do that in the last hour today, right? So we know from the last hour or so that work is the integral of pressure times dV, right? One of the graphs, remember I talked about in sort of all problems that you're going to do in engineering, you want to draw pictures. One of the pictures we're going to find really important, really useful, is a pressure volume diagram like this one, right? Because work is the integral of PdV, which is the area under this curve, right? So in this case, I can't just calculate the area directly because pressure times volume to the 1.5 is constant. I can't do that in my head, so I have to do some calculus. But sometimes I can do it in my head. If the pressure is constant, then it's like a rectangle, right? So I could just calculate the area, right? And if the volume doesn't change, then I have either a line that goes straight up or a line that goes straight down. There is no area under that curve. So if the volume doesn't change, the work is always zero. Right? And we'll see that more as we do different examples. Right? So we know that the work is the integral of P dV. Often, but not always, we're going to be able to look at different processes and say that pressure times volume to some exponent is constant. Now, sometimes I get questions about this, and I apologize for not being super consistent in the slides. Sometimes, really anytime if you see a V with a line through it, I mean volume. The problem is, even though we have lots of letters, we end up using many of those letters for multiple different variables. So sometimes if we were talking about velocity, that would be V, or voltage could be V. So if you see a volume with a line through it, or a V with a line through it, I mean volume. Right? So pressure times volume to the power of N is constant. But I can't put that into my equation yet. Right? What I need first is, so first, you don't need to memorize these things, right? But one of the things that you start to get as you do more and more problems, as you develop this engineering intuition, right, is that things mean stuff, So if you have different values of N, like we talked about this before, if N is equal to 0, then what happens is that P times V to the 0, so that's 1, is constant, right? So if N is equal to 0, that means the pressure stays the same, right? And that's what I mean generically by things mean stuff, which is a terrible sentence, right? But it has a physical meaning, right? So isobaric, iso means stays the same. Baric, like a barometer, right? Bar is a unit of pressure. So isobaric means constant pressure, right? If N is equal to 1, pressure times volume is constant. That means something is isothermal. Iso means stays the same. Thermal is temperature, same temperature. When we start to deal with ideal gases, you'll see that this is the case, that when PV is constant, temperature must be constant too. We'll talk about specific heats. Maybe you've talked about these in chemistry class before, or maybe even in a physics class. Specific heat, which we denote as the letter C, means how much energy do you have to put in to a piece of pure substance for 1 unit of mass to go up by 1 unit of temperature, right? So how much energy, I don't have to put much energy into 1 kilogram of copper to increase the temperature by 1 degree, right? But to increase 1 kilogram of liquid water by 1 degree, I have to put in more energy. So its specific heat is higher. We'll talk about there being 2 different kinds of specific heat, right? One at constant pressure and one at constant volume. They're a little bit different, but if N is equal to the ratio of those specific heats, then this is another one of those engineering decoder ring words. That means the system is approximately adiabatic. Adiabatic means perfectly insulated, right? No heat transfer, right? So one of the things I did in the pandemic, because now you can go in it again, but I don't know if you've ever had a chance to go to the gym here at RIT, but we have a sauna inside the change room, right? And I started doing this a couple years ago. There's a lot of health benefits to the sauna. It just feels good, right? It's good to relax. I think it's good for stress relief. But it was closed in the pandemic, so I built a sauna in my basement, right? I did what I could to insulate that as well as I can, but it's not perfectly insulated. There's still some heat loss through the walls of my sauna, right? So it's not adiabatic, but it's got relatively high insulation, right? If N is negative, what that tends to mean is that the heat transfer is high compared to the work, right? So there is some physical meaning behind what the value of N is, but we don't have to worry about it too much, right? We just know that pressure times volume to the power of N is often constant, right? So we can often look at processes as being polytropic, right? When that happens, I can get an equation for P. So P is equal to C divided by V to the power of N. And I can sub that back into my equation. Then I can start to do some calculus. Right? So when I have this conservation of energy, I know that delta E is equal to Q minus W. I have my picture for what the universe looks like. Right? If I can find work, then what we're going to talk about later is how do we find delta E? And if I can find work and I can find delta E, I'm going to use the first law to find the heat transfer most of the time, right? When you start to take heat transfer class, you're going to be able to find heat transfer directly, and then you could maybe change the order up here, right? So often we'll find delta E by using thermodynamic tables. We're going to talk about this more in the last hour of class today. We know that delta E is equal to the change in kinetic energy plus the change in potential energy plus the change in spring energy plus the change in internal energy, right? So we have this equation for the first law, right? Now, notice this says common assumptions and not assumptions we're going to make every single time. But often in thermodynamics class, we're not interested in kinetic energy. There may be kinetic energy in the problem, like that potato gun problem. The piston is moving at some velocity, but we're going to assume that the kinetic energy change is small relative to the change in internal energy. So much so that if I just assume that the change in kinetic energy is zero, I'll probably get an answer that's in the right ballpark, right? So the change in kinetic energy doesn't have to be zero, but I can usually assume that it's negligible or very small. I can usually assume that the change in the potential energy, the elevation, right, times the acceleration of gravity, is relatively small compared to the change in internal energy. And I can usually assume that the spring energy in the problems that we're going to talk about in this class is also relatively small. So small that it might as well be zero. Right? And if I can make all of those assumptions, which I usually make, right? But for example, if I told you the change in velocity, probably calculate the change in kinetic energy, right? If I can make these assumptions, my first law will often simplify to the change in internal energy is equal to Q minus W. But there's a temptation here to start with this equation down here on an exam. Don't do that. Because if you do that, you haven't demonstrated your understanding unless you write down all this other stuff, right? A way to get in the habit of writing down all that other stuff, the assumptions you're making to build your model, you write down the longest form of the equation first. Tell me what terms you think are not important, and then you'll get the simplified version of the equation. And actually, before I even write down this equation, that delta E is equal to Q minus W, I first have to assume that the system is closed, that there's no mass transfer, right? So that's another assumption we should be writing down, right? So how do I solve the first law? I'm going to write down this equation. I'm going to make some assumptions till I get delta U is equal to Q minus W. I'm going to find the work as the integral of P dV. I'm going to find the change in the internal energy as the mass times the change of specific internal energy. If you haven't looked at the lecture notes for the first 3 lectures, we have this sign convention that capital values are mass dependent, right? So capital letters are mass dependent, like the internal energy of the water scales with the mass, right? So if I have 1 kilogram of water that's at 1 atmosphere and 99 degrees Celsius, if I put 2 kilograms of water at the same state, same pressure and temperature, I have more energy in the system, even though the energy per unit mass is the same, right? So this is like the difference between mass or weight. Both of those things depend on how much mass you have, right? And density, which is the density is the weight per unit mass, right? So that's independent of the mass, right? Or the volume per unit mass, right, is density. Right? Actually, it's mass per unit volume, and then specific volume is the other way around, right? So we're not going to talk about the change in the specific internal energy until the last lecture here. But this is the general flow of how we solve these problems. Is we start with the long version of the first law. We make some assumptions. We get this equation. We find the work as the integral of PdV. And then we're going to do some stuff to find the change in internal energy. And that will let us find the heat transfer. That's basically how we solve all the problems from here until the first midterm. And it sounds easy, but every problem's a little different. Every problem's got its own little wrinkle. But that's why I think it's really important to nail down this process. If you always follow this same kind of flow chart, then you're never stuck wondering, what the heck am I supposed to do? Because you always have a map, right? Now, it's always a little bit different because the pressure volume relationship will be different, right? Maybe the mass is different, so how you find delta U is a little bit different. But generally, you're going to follow the same process for every problem between now and the first midterm. Right? So we use the first law to find Q almost all the time. Now I'm going to do an example today where that's not the case because we don't know how to find delta U yet. Right? So here is our first example problem. So we have a gas contained within a piston cylinder assembly. Right? So this is like that potato gun. Right? And it expands, so the gas is pushing that piston out at constant pressure at 4 bars from some initial volume to some final volume. The volume's getting bigger here, right? And we're asked to find the work in kilojoules, right? So this is the same problem, right? So let's see if I can get this to work. Right, so first I want to find my given information. So we know that there's some gas here, right? At some point that might be important to us, but it's not quite important yet. Right? We know it's in a piston cylinder assembly, so I want to draw this picture, right? We're going from some initial volume to some final volume. The pressure is constant, so I can write this pressure volume diagram, right? We start at some volume, and the pressure stays constant until we get to the second volume. So here, the direction here is positive. I'm going to take my ring off because sometimes it interferes here, right? So we have an initial volume and a final volume, and it asks us to find the work, right? So here we're trying to find work in kilojoules. Now, one thing that I'm going to suggest to you, right, is that there are lots of different units for pressure. Anytime it's a metric problem, I want you to put right off the bat pressure into kilopascals. Right? So here, my pressure, P1, is equal to my pressure, P2, which is equal to 4 bar. Now, maybe you haven't looked at those first 3 lecture notes yet. One of them will talk about all the different units we have for pressure. Bar is a unit of pressure. Now, you may or may not know this, but atmospheric pressure in the metric system is approximately, now it changes, right? You might look at a barometer to sort of give you some indication of the weather, but it's about 101.3 kilopascals. The metric system hates this, right? Because the metric system likes nice round numbers, right? So 1 bar is approximately equal to 1 atmosphere, right? But it's actually equal to 100 kilopascals. And now the metric system feels better because it's a nice round number, right? So if I want to convert bar into kilopascals, I take this and I know that 100 kilopascals, because kilopascals are the units I want on the top, is equal to 1 bar. Bar is the unit that I want on the bottom. Right? Now, just like it's math, I cancel out the units here. And now I see that my pressure is equal to 400 kilopascals. So this is P1 and P2. I would suggest to you, anytime you have a closed system problem that's where the units are metric, that you make this conversion right away. Don't even think about it. Just when you write it down, you want your pressure in kilopascals, right? Because if you have a volume times a pressure, now, and also, I guess I'll show you why, right? So here we know that the work is the integral of P dV, right? Which is kind of like pressure times volume, right? So if my pressure is in kilopascals, that's kilonewtons per meter squared, and my volume is in cubic meters, what happens now is I can take meters cubed divided by meters squared and I get meters, right? And this becomes kilonewton meters, which is kilojoules. That's what I want, right? If I didn't do that and I had this as bar times meters cubed, then I get this nonsensical unit that's bar meter cubed. Technically, that is energy, right? But it doesn't make any sense, right? So if it's a metric problem, always convert to kilopascals. If it's an imperial problem, it's even worse because probably your pressure is going to be pounds per square inch and your volume is going to be cubic feet. So you're going to have to do some kind of unit conversion between inches and feet, right? So now we want to find our energy in kilojoules, right? So there's not too many assumptions that we have to make here, but there's some that they told us, right? They were assuming that pressure 1 is equal to pressure 2, right? In real life, it's probably not exactly this clean, right? It probably doesn't exactly work like this. There's something happening to keep that pressure constant, right? But it's probably not exactly constant. It probably bounces around a little bit. This is more important, the assumptions, when we start to talk about the first law, right? Now, the governing equation, because what we're trying to write down here is we want the equation for work, right? So here we're going to see that work is the integral of P dV from V1 to V2. This is my second favorite kind of calculus, right? The easiest work problems are ones where the volume, if the delta V is equal to 0, right? So if I had a pressure volume relationship where I was, we'll pretend that's a vertical line from state 1 to state 2, then there is no area under that curve, right? So then in this case, work would be 0, right? But that's not the situation we have. Instead, we have this constant pressure. That's my second favorite process here, because it means I could get this answer without doing calculus, because the work is the area under this curve. There is a little bit of danger, or I can say that work is equal to the area under my PV diagram, right? But if I do it this way, I got to remember that if volume goes up, then work is positive. And if volume goes down, that means work is negative. That's why I drew this arrow here to remind me that I'm expanding. Because I'm expanding, I'm expecting work to be greater than 0. That's one of the things we can check at the end of the problem to see if we have confidence in our answer. We always want to check our units, and we want to kind of check our sign. So I know that work is the integral of P dV. Right? So this is where I'm going to start. Work is the integral of P dV. Right? Here I know that P V to the N is constant. Right? But P is equal to C over V to the N. Right? That's what I'm going to put in here. Right? So I'll do this, you don't have to do it this way in this case because it's a little simple. But I'm going to do this just to show you that you can always do it this way. Right? So here from V1 to V2, I have some constant over V to the power of N dV. Right? But the good thing for us is that we are told that N is equal to 0 because the pressure is equal to a constant. What that means is that I have the integral from V1 to V2 of some constant times dV. This constant, it's equal to P1 and it's equal to P2, right? So here I can make this the integral from V1 to V2 P1 dV. This is my second favorite kind of integral because our, I don't know. We're not going to get rid of that. Because our pressure is not a function of the volume. So I can pull it out. Right? So this is going to become P1 times the integral from V1 to V2 dV. If you were doing this on a test, you might skip some of these steps, but always write down that work is the integral of P dV. Always tell me what the pressure-volume relationship is. Right? This is really just going to be P1 times V2 minus V1. Here we can see that because our volume is expanding, right? V2, I know right now that V2 is bigger than V1, which means work should be positive, right? Which is good because that's what I expected because I knew it was expanding. So the math kind of agreed with my intuition, with my understanding of what's going to happen here, right? Now here, my pressure, so this is the other thing that people often make mistakes on, right? Is keep the problem symbolic for as long as you can. And anytime when you start to put numbers into an equation, you also have to start to put in variable, or you have to put in units, right? So if you don't like units in your calculations, which you probably don't, keep it symbolic for as long as you can, right? But now I know that P1 was 400. Oh, I don't know why it's highlighting it like that. P1 was 400 kilopascals. Now this is going to be, I got to go back to my given information to find out what V2 and V1 were. V2 is 0.36 meters cubed and V1 is 0.15 meters cubed. So this is 0.36 minus 0.15 meters cubed. Now, I remember that 1 kilopascal is equal to, kilopascal is kilonewtons per meters squared. So now I'm going to multiply the numbers, but I also have to multiply the units together. So when I take meters cubed and divide it by meters squared, it just becomes meters. So my units over here are going to be kilonewtons times meters, right? And my numerical answer, if I put it in my calculator, I get 0.36 minus 0.15. Right, that's going to be 0.21. So here I won't skip the step. I'll say that this is going to be 400 times 0.21, and that's going to equal 84. So plus 84 kilonewton meters. I know that a newton meter is a joule, so this is going to be kilojoules. And that's the work, which is what the problem asked me for. Now here I can go back up and check. I can say, well, it asked me for work in kilojoules. I got work in kilojoules, right? If I didn't immediately change my pressure to kilopascals, here I would have gotten bar meters cubed. Or what I sometimes see on exams is people don't write the units in their problem, and they take 4 times 0.21 and they get 0.84. No, they get 8.4, right? And they just leave it as 8.4. They don't even tell me what the units are. And that's not demonstrating your understanding of the process, right? It's because you did something wrong in that case, right? So you need to carry your units in once you put numbers in, right? So here we get, so here I want to verify. I have no idea if, maybe if I was an engineer that worked in problems like this all the time, I would have some concept of what the number should be, right? Like in the first 3 lectures, it talks about pressure, right? So if you're a scuba diver, you might know that for every 10 meters you swim down in water, the pressure goes up by about 1 atmosphere, right? But if you're not a scuba diver, you don't know that. So you don't necessarily know if the magnitude of the number makes any sense, right? But I can still check 2 things, right? So one, I can check the units. The problem asked me for kilojoules, and that's what I got, right? So that gives me confidence. I don't know that my answer is right, but I can't prove that it's wrong. That's not the same thing as being right, but it's better than proving that I'm wrong. Like if I got an answer here of like kilojoules times meters, I know that's not right. Or kilojoules per second, I know that's not right. So I can't prove that I'm wrong here. That's good. The second thing that I can check is, does the sign make sense? Right now, here in our piston cylinder assembly, as we moved from state 1 to state 2, the volume got bigger. When the volume gets bigger, it means that the system is pushing out on the surroundings. So we know from hip to win that work in is negative, but this is not work in, this is work out. This is the system doing work on the surroundings, it's pushing out on the surroundings. So that means we expect work out to be positive, right? So here I'm expecting this to be positive, and it was positive, right? So I don't know if my answer's right, but my confidence is reasonably high because I got the right units and because the sign was correct. Does anybody have questions about the first example that we just did? Yep. You can unmute or write in the chat, whatever you prefer.
Yeah, I guess I'm a little confused on the PV to the N equals C part of this.
Yep.
Yeah, would you mind going over that?
Sure. So often we have polytropic processes, which means that we can say for this process, it's not always true, right? So I just put this in. You could have skipped this step on this problem, right? But I want to get us in the habit of doing this, right? So this is a problem where the pressure is constant, right? So here, because the pressure is constant, that must mean that N is equal to 0. And if N is equal to 0, V to the 0 is equal to 1. So I could have just said, right from here, right from the jump, I could have said pressure is equal to constant, which is P1, which is equal to P2. I could have skipped this and come right down to here. But we'll see in the next example where, like, if we had a problem that was PV to the 1.5 was constant, then I can't do that. So here I put these intermediate steps in here just to kind of lay the groundwork for the next example, which is a little trickier. But in this case, you didn't have to do these lines over here. Does that make sense?
Yeah, thank you so much.
You're welcome. It's a good question. So when we're trying to find work and it's a closed system, we know that the equation we need is W is equal to the integral of PdV, right? Which means that we need to be able to do some calculus. But maybe we'll get a case like this where it's not that much calculus, right? Or like I said, maybe the volume doesn't change and then it's not calculus at all, right? So if you want to go through, I'll just kind of look at these quickly, right? But if you look at the notes that I've posted, they're basically these PDF notes. So you can see that I go through the problem, and I think it's better if I do it by hand versus kind of animating it through PowerPoint, right? Now, sometimes we might have to do it the other way, but when we have time, I would like to do it this way, right? But if you want to look in the notes, then you can see that this is the same thing, right? So this is our second example, right? And now this one is going to be a little trickier, and it's a whole first law problem, right? So a gas in a piston cylinder assembly is compressed from P1 is equal to 3.4 bar at a volume of something, right, to some higher pressure. And it tells us here that the pressure volume relationship is PV to the 1.2 is constant. That means this is not a problem that I can do just by knowing the area, because I'm going to have to do calculus in this problem, right? Now, the mass of the gas is also given. During the process, we're also told the heat transfer, and we're asked to find the change in the specific internal energy of the gas, right? We're told that we can neglect kinetic and potential energy effects, right? So we'll do this problem too, right? And again, if you want these, I think I just posted PDFs, but if you want these problems written out, you can grab them off my courses, right? So here, we know we're given V1. Oops. Sorry about that. We're given P2. So we know V1. We don't know V2, right? But we do know P2. We know P1. We know that PV to the 1.2 is constant. We know the mass of the gas. And we know that Q, well, we know the magnitude of the heat transfer is 2.2 kilojoules. Here it says the heat transfer from the gas is 2.2 kilojoules. So if I was drawing this on my diagram of the problem, I like to draw Q as like a wavy line like this. Heat is leaving my system, right? So whenever you pull numbers from a problem, we have to think about the signs as well, right? So who thinks that this heat transfer is, this works better in a room, right? So who thinks that it's positive? Who thinks that it's negative, right? So try, you don't have to tell me what you think, right? But before I write it down, just make a guess. And this is kind of like all science, right? Science is about testing hypotheses. It's okay if your hypothesis is wrong, right? It's about learning, right? So here, we know we have this mnemonic thing that tells us that heat in is positive and work in is negative. This is heat out, right? So it's always, we're like standing inside the system. So heat is leaving the system for us. So here we know that Q should be negative 2.2 kilojoules. Right? The other thing that I want to do is I want to convert my pressures automatically to kilopascals. So this is going to be 3.4 bar times 100 kilopascals per bar. Bars cancel, right? So this is 340 kPa. P2, same thing. I got to take this 8.2 and I got to multiply it by 100, and this becomes 820 kilopascal. I also want to draw my PV diagram. Here again, I cheated because I got this computer generated version of this. But on a test, you just sketch this out. It's fine if you don't get, even if you don't get the curvature correct, you know, if you drew it this way, you just want to kind of draw what's going on, right? And I always want to show the direction. So in this case, my pressure is going up, right? Here, without even doing the math to find what the volume is yet, right? So I can also see from this that P1 V1 to the 1.2 is equal to some constant, which is equal to P2 V2 to the 1.2, right? Which means that P1 V1 to the 1.2 is equal to P2 V2 to the 1.2. Does that make sense? So what I know is if the pressure goes up, the volume has to go down, right? So that's what's happening here. This is my state 1, and this is my state 2, right? So P2 is bigger than P1, but V2 has to be smaller than V1. If I'm not comfortable just sort of intuiting that from this, I can also find V2 pretty quickly here. I can say that V2 to the 1.2 is equal to P1 over P2 times V1 to the 1.2. I'm kind of running out of room here. Right? Sorry, I'll draw this down here, right? So I can make this, I could say that V2 is equal to P1 over P2 times V1 to the 1.2, all divided by 1 over 1, or all to the power of 1 over 1.2. That would give me a value for V2. Right? I'm not going to calculate that right now, but I could. Right? What this problem wants me to find is the change in the specific internal energy. When I write the word specific in front of a term, right? So U, big U, is equal to internal energy, right? Little u is equal to specific internal energy, right? And I know that delta big U is equal to the mass times delta little u. So for us, uppercase letters and lowercase letters mean different things. Uppercase letters are extensive properties, properties that change with the amount of mass that you have in the system, like weight. Lowercase letters are intensive properties that don't change with the amount of mass that you have in the system, like temperature, right, or density, right? So here we want to find delta little u, right? So we want delta u, and they tell us that we want this in kilojoules per kilogram. So now, we want an equation that has change in internal energy in it. The only equation that we know of that has change in internal energy is the first law, right? So here, I need to write down my whole first law, right? And I'm going to make some assumptions. I'm going to say, I don't know anything about the change in velocity here, so I'm going to assume that delta KE is much less than delta U, right? And delta PE, right? Another way of saying this is that it's approximately equal to 0, right? And that's approximately equal to the change in kinetic energy. So all three of those terms, they might not actually be 0, but we're going to say they're so small compared to the change in internal energy that I'm just going to get rid of them, right? So then here, my first law becomes U2 minus U1, oops, this big U1, is equal to Q minus W. But I don't want the change in internal energy. I want the change in specific internal energy. So this is M times little u2 minus little u1 is equal to Q minus W. So that's good. I've made some assumptions and I made some simplifications, right? The good news here is that I was told the heat transfer. I had to think about the sign, but I know the heat transfer. I also know the mass. I'm not going to find U2 and U1 individually. I'm going to change this back to delta U2, or delta U, I'm sorry. The bad news is, right, so I don't know delta U, right, but that's what I'm going to try to find over here, right? This is the required thing to find, right? The other bad news is I don't know the work. But thankfully, I do know that work is the integral from V1 to V2 of P dV. So if this is equation 1, and this is equation 2, if I can get an answer for equation 2, I can sub that into equation 1, and I can get an answer for delta little u. Does that part make sense? And the good news is we have at least now some small experience trying to find work. So we know that work from 1 to 2 is the integral of P dV from V1 to V2. Now, in the last example, we could have skipped, like we said, we could have just said, oh, the pressure is constant. And we could have just put this constant in and pulled it out of the integral. But in this case, the pressure is some function of the volume. So we have to do some calculus. In fact, we know that PV to the power of 1.2 is constant. What that means is that pressure is equal to that constant divided by V to the 1.2. And I can put that back into this equation, right? Because I can't do the integral if I don't have it as a function of volume, right? So now this is going to become the integral from V1 to V2 times this constant divided by V to the 1.2 dV. Now, this is not a subscript here. I just messed up. For me, I prefer to do the calculus if I rewrite this a little bit as V1 to V2 of C V to the negative 1.2 dV. Good news is that the constant can come out. So this becomes c times the integral from v1 to v2 of v to the negative 1.2 dv. This is the part at the beginning of the class where I always get a little nervous because I actually have to do some calculus here. Right? So when we integrate, right, so we take c, we're going to add 1 to the exponent. Right? So this is going to become v to the negative 0.2. And we're going to divide by the exponent we have left. Right? So this is going to be negative 0.2 from v1 to v2. There is a temptation here to start plugging in numbers right away. But I'm going to avoid that temptation for now, and I'm going to show you why. Because when we do that, we'll get a generic solution for when n is not equal to 1. Right? So here we're going to keep this as c. This is going to be v2 to the negative 0.2 minus v1 to the negative 0.2 divided by negative 0.2. Now, this could just be me, right? I'm an engineer and I like things in a particular way. I don't have this problem, but I know that some people, some of my colleagues, if they go into a house and the paintings are like askew, they feel the need to straighten them out. I don't like negative numbers in my denominators. So I'm going to multiply that fraction by negative 1. Right? So I'm going to get rid of the negative number in the denominator and I'm going to flip the order of the terms in the numerator. So this is going to be this constant times v1 to the negative 0.2 minus v2 to the negative 0.2 divided by 0.2. Here's the sleight of hand. What I know is that PV to the 1.2 is equal to a constant. That means that the pressure at 1 times the volume at 1 is equal to the constant. But it's also true that the pressure at 2 times the volume at 2 to the 1.2 is constant. Right? So here, my equation is actually C V1 to the negative 0.2 minus C V2 to the negative 0.2 divided by 0.2. What's going to happen is, in this first instance of C, I'm going to use P1 V1 to the 1.2 because it's multiplied by V1. But in the second instance of C, I'm going to use P2 V2 to the 1.2 because it's multiplied by V2. It might be a little while since you've done arithmetic, right? But if you multiply together V to the N times V to the M, all you have to do is add together the exponents. The beauty in this case is that I have this. I won't skip the step. So now I'm going to have P1 V1 to the 1.2 multiplied by V1 to the negative 0.2 minus P2 V2 to the 1.2 times V2 to the negative 0.2 divided by 0.2. But when I multiply these together, I add up the exponents, and this is just V1. And this is just V2. And I could think of this as n minus 1. right? Because n was 1.2. So generically, what's going to happen is if n is not equal, if n is not equal to 1, I'm going to get P1 V1 minus P2 V2 divided by n minus 1. You can always go through the calculus, but if n is not equal to 1, this is what you'll get. If n is equal to 1, it's a little trickier because your integral is going to be 1 over v dv. And when you integrate that, you'll get the natural log. So it's a little bit different in that case. So in this case, I can find my work is equal to P1 V1 minus P2 V2 over 0.2. I know, if I remember correctly, I knew what P1 and P2 in V1, and V2 was going to be equal to P1 V1 to the 1.2 over P2, the 1 over 1.2. So I can sub that in here, right? And that will give me an answer for the work. We'll go through the math and I'll show you in the slides what the number is. But this is good because now this was, I believe, this was our equation 2, right? And then our equation 1 was m times delta U is equal to Q minus W over, it's just equal to Q minus W. But what we want is delta U is going to be Q minus W over the mass. Here, this 0.2 has no units. Here, because, so this is pressure times volume minus pressure times volume. My pressure is in kilopascals again, which is kilonewtons per meter squared, multiplied by meters cubed. So this is going to be kilojoules. Both of these terms are kilojoules, right? So work is going to be in kilojoules. Heat was in kilojoules. Mass was in kilograms. So here we're going to get an answer that's in kilojoules per kilogram, which is what we wanted, energy per unit mass. So we'll see when we get the number. I don't know off the top of my head if this should be positive or if it should be negative. Because here's what I know. I know that the heat transfer term was negative, right? Because we were losing heat from the system. Now, work was going in, right? Because our volume was going down, which means that work is less than 0. So this is going to be a negative number minus a negative number, right? So this, the work term, is going to act to increase the change in kinetic or in specific internal energy. And the heat transfer term is lowering the change in specific internal energy. So it's good that I got the units right, but in this case, I don't actually know what the sign should be. I don't have any intuition about whether it should be positive or negative. Right? If I go back to the slides over here. So first, for this part, for the derivation part, does that make sense? Or does anybody have a question? The trick here, two things that I think are tricky. The first is that we actually had to do the calculus for the work, right? So we always want to cast pressure as a function of volume so that we can put it in here. And then if it's not equal to 1, you're going to be able to use this equation. You can memorize this equation, or you can just do the calculus, right? But it's always kind of even if you do the calculus, it's nice to know what the shape of the answer at the end should look like, right? And then you put it in. But here, because we actually did the first law, we also had to make some assumptions over here to get to mass times delta U is equal to Q minus W. And then we put the work in. So now if I come back to my assumption, right? So here we were doing our work, right? So this was the same equation we got for work before. When we started to put numbers in, I had to find my second volume, right? So I used that same equation because I know PV is constant and I know P1, V1, and P2. That means I can isolate for V2. In this case, I got 0.0136. I don't know if that answer is right, but it is an answer in cubic meters. And it's smaller than V1, which is what I think the problem is telling me, because it's telling me it gets compressed, that the volume gets smaller. So I have some confidence in this answer. Then here, when we put those numbers into our work equation, we get negative 7.65 kilojoules. Work ended up being negative, which is good. That's what I think should happen because the volume is getting smaller, so work should be negative. But then when I put that in here, right, this is a negative work. So this is another thing that people often will get wrong in exams, is when work is negative, it means I put a negative number in here, right? So then it's minus a negative number. So that negative work acts to store energy in the system. Just think, if there was no heat transfer happening and I compressed the system, I'm storing some extra energy in my system because I'm increasing the pressure, right? So we got to remember that we put that sign into W, and that flips the sign here. Another thing people might make the mistake on here is, here it tells us the direction and the number, but we have to put that sign in, right? So that was another thing that people could make mistakes on. And then I get an answer. Now again, I don't know if this answer is correct or not. I don't even know if the sign should be right. So the two things that I like to try to check at the end are, does the sign make sense? I don't know. Because I have opposing things where the heat transfer should be lowering the energy in the system and the work should be increasing the energy in the system. So I don't know, just from reading the problem, which of those two, it's a tug of war, and I don't know which one's winning. So here, this problem tells me that it's a positive number, right? I don't know if that's right or not, but I do know that the units are correct, right? And again, I checked the volumes on the way, so that gives me some more confidence. This actually isn't the answer to the problem, right? Because this is just the change in the internal energy, and the problem asked for the change in the specific internal energy. So I needed to go back and divide by the mass, which is 0.183. So here, if I take this, I should take this and then say this, and then if I put this into my calculator, 5.45 divided by 0.183, I get 29.8, and this is in kilojoules per kilogram. And this may be a tip in case you ever have to write lab reports. If you press Alt and then equals in any Microsoft product, you'll get this equation editor. And when you're in equation editor, right, so here, you know, I can write this kind of slash over here. I never remember if it's slash or, and let's say I wanted a sigma, right? It just turns into sigma, right? Or lambda or whatever. Or if I want, you know, a fraction, I just go like this, right? So I think that's a useful thing. So does anybody have questions over about the second example that we've done here? Kind of makes sense? Why is 2.2 negative again? So this is a really good question, and it's good to nip it in the bud right now, right? So here I'll go back to the other. So it's telling us the heat transfer, right? But it told us that the heat transfer is going from the gas. So our system is over here. Our system is the gas. Heat is it's saying it's from the gas, right? So that means when I draw it on my diagram, it's going from the gas to the surroundings. That's heat out of my system. From my sign convention, heat in is positive, but heat out is negative. Does that make sense? You're welcome. So that's so we got to think about the signs of things. And again, so it's always good to draw these PV diagrams and the direction, and we know if the volume is increasing, work is positive, and if the volume is decreasing, work is negative, and if the volume doesn't change, there is no work. So with that, we're sort of through our second set of our second hour here, and we got about an hour left, so we can take a break for maybe 5 minutes or so. Maybe we'll come back at 8:55, and we can go through the third part of the lecture, which will be how do we calculate internal energy, or how do we find it. Thanks, everybody. We'll be back in whatever it is, 6 minutes. start back up in a couple minutes. Okay, welcome back, everybody. So, again, we've been talking about the closed version of the first law, because that's the version of the first law we're going to use between now and the first midterm. So, we have these three questions. What's in the system? It will either be something like water or some kind of ideal gas. Then we ask ourselves, is the system open or closed? It's always closed until we get past the first exam. And because it's closed, we can write down that delta E is equal to Q minus W. Then we're going to ask ourselves what happens to the system. That means what's going on with the work and what's going on with the heat transfer, right? Is there something about the pressure volume relationship that I know about, right? So when I know all that, I should be able to solve the first law. Right, so delta E is equal to Q minus W. We're going to often, but not always, assume that changes in kinetic, potential, and spring energy can be neglected. That means that delta U becomes Q minus W. To find the work, I take the integral of PdV. And then I've got two things that I don't know, which is not great, right? Because ideally, well, really, if I want an answer, I need to have as many equations as I have unknowns, right? And if I think about this as delta U on the left-hand side, I have three different unknowns, but I only have two equations because I have an equation for work and I have the first law, right? Sometimes this is okay, right? So we have something that we call a simple system. Simple doesn't mean easy. Simple means less complicated. So in thermodynamics, we talk about processes that have heat transfer and work, right? That the change in the energy in the system is because heat transfer and work are both happening. But in a simple system, only heat transfer or work happens. So we can either assume that it's adiabatic, that there is no heat transfer, or that it's passive, that there is no work, right? This is not bad in the case where it's adiabatic, because now my first law gets simplified to delta U is equal to negative work. And I got an equation for work, it's the integral of PdV, right? So I could find delta U from the first law, only knowing work if it's adiabatic, right? Because I could say, oh, work is the integral of PdV, and if I know the pressure volume relationship, then I could find U. That's great, or change in U, right? It's not that good if the system is passive, right? If that means that there is no work, or that the work is much smaller than the heat transfer. Because of the three terms in my equation, the only one that I know how to determine right now is work. So if I cancel that one out, I'm kind of not in a good place. I used to have three equations and one unknown, or three equations and I used to have three unknowns and two equations, but now I have two unknowns and one equation, so I'm no better off, right? So in this case, I don't know either. So we need to develop some sort of strategy for finding internal energy, right? Like I said, as you move on through mechanical engineering, you'll figure out different strategies to find heat transfer. But for now, we're only going to find heat transfer from the first law. So you need to be able to find work in a closed system, and you need to be able to find the change in the internal energy. So we know that work is the integral of PdV. We can say that the change in the internal energy is the mass times the change in the specific internal energy, but that doesn't necessarily help us right off the bat. It gives us another equation, but it introduces some more unknowns, right? But our general strategy, our flow chart for determining first law problems is going to be assume that it's closed, write down the whole first law, make some assumptions so we get to delta U is Q minus W, work is the integral of PdV, and then we find the change in internal energy as the mass in the change times the change in specific internal energy, and then we use the first law to find the heat transfer. Generally, that's what we're going to do. But to do that, we have to be able to find the change in the specific internal energy, right? So unfortunately, it's not that easy to measure internal energy or specific internal energy, right? This is the energy that's somehow related to the energy that's stored in the mass because of things like its temperature or its pressure, right? Remember we saw those metal pins, right? That was really hot, right? So it changed temperature, right? Like you don't want to go ahead and you don't want to go touch that, right? You probably learned real young not to touch the stove when it's glowing, right? It's not easy to measure internal energy. But the good news is we don't have to measure internal energy. And that's because, again, if you look at the notes from the first 3 lectures, which I strongly encourage you to do, it talks about thermodynamic states. And the beautiful thing about a thermodynamic state is that once you know 2 independent intensive properties, so those are 2 properties where you don't like. So first, an intensive property is a property that does not depend on mass, right? Like density or temperature or pressure. If I think about half of the room that I'm in or all of the room that I'm in, the temperature is the same, right? But the mass of the air is different, right? Or the weight of the air is different, although it's pretty small, right? So I want to be able to find the state, because once I have fixed the state, right? Once I know the state, I know everything about the mass that I'm talking about. So I need 2 independent intensive properties, right? So if, like on this example, right, if I knew the pressure of something, so pressure is not dependent on mass. So if I know the pressure and I know the temperature, then I could find the specific internal energy, right? So in the back of the thermodynamic textbook, or also located in the My Courses website, you'll find a whole bunch of thermodynamic tables, right? Both in metric units and in imperial units, right? Now, if we can know enough about a material, some sort of pure substance, at a given temperature or pressure, if I know 2 independent intensive properties, I should be able to fix the state. And once I fix the state, I know everything about that material, right? So this is superheated water vapor. That means steam. So water that's above the boiling temperature for a given pressure. If I'm trying to find the specific internal energy and I know the pressure and I know the temperature, then I can find it on this table, right? So we're going to start talking about how we use these tables to find U, right? Now it takes some doing, right? It's not a simple thing, but we're going to start today, and then we're going to take a bunch of time between now and the first exam to get familiar with how to do this, right? So a thermodynamic state is anytime you have your system at equilibrium, that means nothing is changing with time, then how much energy is in that mass is only a function of its thermodynamic properties. Right? So thermodynamic properties are things like pressure, temperature, specific internal energy, specific volume, right, which is volume divided by the mass, right? If we can fix the state, if we know the state, then we know everything, right? And that sounds like it's almost impossible to do. How can I know everything about this state, right? But the good news is I only need two properties, provided those two properties are not dependent on mass. So things like pressure and specific volume, and that those two properties are independent, right? So intensive properties don't depend on mass. So things like temperature, pressure, density, or specific volume, right? So density is mass divided by volume, but specific volume is volume divided by mass. That's a good example of two properties that are not independent, because one is just the reciprocal of the other. So if I ever tell you the density, you know the specific volume automatically, because you just have to invert that number, right? So if something is dependent, then that means once you know one of those things, you automatically know the other one of those things, right? So rho, which is density, and specific volume are dependent, because anytime I give you the specific volume, you can automatically find the density, or the other way around, right? But if properties are independent, then just because I know one doesn't mean I know the other. Anytime you know the pressure and the specific volume, then you can fix the state. Unfortunately, you can't always fix the state if I tell you the temperature and the pressure, because sometimes temperature and pressure are dependent. Water, when it comes out of your tap and it's a liquid, temperature and pressure are independent. And if you heat it up, they stay independent until you start to boil. Because I can then tell you, if you're at 1 atmosphere, the water will boil at 100 degrees, but I don't know. So if you know that water is at 1 atmosphere and 100 degrees, you don't know if it's liquid, or if it's all steam, or if it's some combination of liquid and steam, right? So you won't know what's going on there, right? And one of the ways we can see that is by starting to draw phase diagrams. If we take any pure substance, right? So a pure substance is just, right? So a substance that's only got one kind of molecule in it, right? So it's just water. It's not salt water, right? It's just H2O, right? And then we can draw this kind of three-dimensional space, right? And in this three-dimensional space, we have three different variables. We have pressure, right, on the vertical axis in this diagram. We have specific volume, which is the volume divided by the mass. And we have the temperature. Any particular state point is just one point on this three-dimensional surface, right? In this three-dimensional space, right? So this is a PVT space, or a PVT surface, right? And this diagram has some single-phase regions and some multi-phase regions, right? So what do we mean by phase, right? So phases of matter that we talk about in this class are solids, liquids, and vapors, right? There's also plasma, but we don't talk about plasma in this class, right? So in this diagram, right, so if you think about water, water can be ice, it can be liquid, or it can be steam, right? It's all just H2O, right? But depending on the temperature and the specific volume and the temperature, it can be in any one of these different phases, right? Or maybe two of these phases together when you're making your mac and cheese and you start to boil the water. If you had like a piston on top to catch it, right, you would have some steam, some water vapor, and some liquid water. So you'd have some combination. That would be two-phase, right? In this three-dimensional diagram, sometimes there's only one phase present. Like you could have a solid, like solid ice. Sometimes you only have liquids. Sometimes you only have steam. Right? But remember, the genesis of thermodynamics is about this steam engine. Right? We're putting in heat to get work. So for a long, long time, when you give mechanical engineers heat, the thing we want to do is boil water. Right? And I remember how it was kind of disappointing to learn that, you know, sort of the pinnacle of human ingenuity, which is like a nuclear power plant, it's just a steam engine. Right? Now it's a super sophisticated steam engine, you know, and that nuclear reaction generates so much heat, right? So some mechanical engineer was sitting around and saying, oh, we could use all that heat to boil a bunch of water, make some steam, and run it over a fan, right? And then we can get some power, right? So much of the work that we're going to do in this class deals with this two-phase region when we're moving between a liquid and a vapor. Boiling water is a big deal for us in this class, right? Because it's super important still. You know, we're reducing our dependence on coal power plants, but they still exist in the United States. Coal power plants burn coal to boil water. We still have nuclear plants here. Nuclear plants take this nuclear reaction to generate heat and boil water, right? So boiling water is important for us, right? Now, anytime we're looking at this process of boiling water, we're in this two-phase region. So you can have some equilibrium points where you could stop whatever's going on, totally insulate everything, and have liquid water and water vapor or steam coexist, right? So if you were right at the right temperature and pressure, so if you were right at 1 atmosphere and right at 100 degrees, you could have half of your mass as steam and half of your mass as liquid, and they would just stay that way, provided you could make it so you're not gaining or losing heat, right? Here we call it being under the vapor dome because this looks a little bit like a dome shape, right? It's like this dome, right? And under the vapor dome, temperature and pressure are dependent, right? So if I tell you water is boiling and the pressure is 1 atmosphere, automatically you know that the temperature is 100 degrees Celsius, right? Well, or at least you could look it up on a table, right? So under the vapor dome, we're interested in this new kind of property. We call this property quality. So quality is the mass fraction of vapor divided by the total mass. So it's like the percentage of mass that you have that's steam versus liquid. So if you have a high quality steam, it means that you don't have very much liquid water, not a lot of little water droplets in there, mostly steam. So there's more energy in there, right? So if you were running a power plant, you'd kind of want to boil off most, if not all, of the water, right, to get higher quality steam. So that's why it's quality, right? So here, as we move from left to right, and it makes more sense when we start to look at two-dimensional diagrams, we'll go from liquid, which is over here, to vapor, which is over here. And quality only exists if we're under the vapor dome here. So there's some special points or special lines, I guess, on these curves where we have liquid water that's at the right temperature and pressure to boil, but it's still liquid, right? Or steam that's at the right temperature and pressure to condense, but it's still steam, right? So if we have quality equal to 0, that means we're just about ready to boil, but we haven't boiled yet. It's liquid water, but it's at just the right temperature and pressure that it would boil, right? So what that means is, there's these water molecules, right? And the water molecules have some forces that are keeping them close together. That's why it's liquid water. But as you increase the temperature, the water molecules start to move around more and more and more and more, right? And eventually, the temperature gets high enough that those water molecules separate enough to be a vapor, right? And if you have only vapor in your mixture, but you're still at 1 atmosphere and 100 degrees, then you have a quality of 1. So you're at the right temperature for boiling and condensing, but you only have steam, right? No liquid. The other thing about the vapor dome is the top point is called the critical point. The critical point is the highest temperature the temperature related to the critical point is called the critical temperature. And that's the highest temperature where water and water vapor can coexist at equilibrium. Right? Similarly, the critical pressure is the highest pressure where water and water vapor or steam can coexist at equilibrium. If you take a material science class, they'll probably start to talk about, how you can heat treat different steels and get different properties. And they'll draw phase diagrams like this, pressure versus temperature diagrams. Right? And here our phase transitions are lines, right? So here, everything over here is vapor. Everything in this part over here is liquid, and everything over here is solid. But the boundaries between solid and liquid is just a line, and so is the boundaries between the other phases. Now, when we're talking about thermodynamics for mechanical engineers, we're often talking about boiling water. So we're really interested in this liquid to vapor transition, and drawing a pressure versus temperature diagram kind of flattens out all that information. So we're really interested in what happens on that line. So we basically never draw these pressure temperature diagrams, which are really just slices out of that three-dimensional PVT space. Right? So we don't really care too much about pressure versus temperature diagrams, right? Because as mechanical engineers, what we're often interested in, especially historically, is when we put heat in by doing something like burning coal, if we put that into water, we boil it and get steam. We force that steam over something like fan blades, right, in a turbine to make some kind of shaft spin. So now we've gone from heat energy, which was originally stored as chemical energy, into mechanical energy, something moving, right? And that's how a locomotive engine works, right? Any steam. It's also how a nuclear power plant works, right? So things that we are interested in are PV diagrams and TV diagrams. So we're interested in having specific volume on the x-axis and sometimes pressure on the vertical axis and sometimes temperature on the vertical axis. This is going to take some practice to learn how to draw these things, right? So we're going to want to know, so anytime you have these, you want to draw, if you're talking about water or something like it, so maybe a refrigerant, you're going to want to draw a vapor dome. But then you also want to know on a PV diagram, what does a constant temperature line look like? So a constant temperature line goes down and to the right, and any time that line hits the vapor dome, then if you're at constant temperature, it's flat under the vapor dome. Right? Similarly, on a TV diagram, you still want to draw a vapor dome, but now you want to know how a constant pressure line works. Right? So a constant pressure line is going to go up and to the right. That's the difference here, is that here it's going up and to the right, but it's still flat anytime it hits the vapor dome. Right? So here, if this is 1 atmosphere, right, water comes out of my tap, maybe it's at 20 degrees. That's pretty hot to come out of your tap. It's usually colder than that. You heat it up on the stove, right? Then it starts to boil, right? The temperature stays the same, right? And the pressure stays the same. If you're at constant pressure and you're boiling, you're also at constant temperature until you've boiled all the liquid, and then the temperature starts to run away. Right? So if we want to fix a state, we want to put a dot on one of these diagrams. Right? So we need two independent intensive properties. Sometimes, if I know temperature and specific volume, sometimes those two things will meet at a point. Well, if always here you can see if I know temperature and specific volume or pressure and specific volume, if I draw a constant temperature line and a constant pressure line or a constant specific volume line, they always meet at a point. A constant pressure line will be horizontal here. A constant specific volume line is vertical here. They're always going to meet at a point. But if I draw a constant temperature line at 100 degrees Celsius and a constant pressure line at 1 bar or at 1 atmosphere, they don't meet at a point. The intersection is a line. And that's why sometimes temperature and pressure are dependent. Does that idea make sense? If we're at the boiling temperature for a given pressure, we need more information to fix the state. Right? And one of the things we can know about is quality. What percentage of my mixture is vapor? So it's a bit of a tricky idea. It's okay if it doesn't make 100% sense now, but as we move through problems, we're going to see this more and more often, right? So when I look in the tables, right, because I talked about we're going to find specific internal energy by looking it up in tables. So when I'm talking about water and I'm looking these things up at the tables, I want to know what the phase is. So I want to know if it's solid, liquid, or vapor. The good news, or some combination, the good news in this class is never solid water. So we really want to know if it's liquid, vapor, or some combination of liquid and vapor. So you never are going to have to draw a TV diagram or a PV diagram that's to scale like this one. But this one's kind of there to show you, right? So here I have different regions on this diagram, right? So if I'm to the left of the vapor dome, or to the left of the critical point and above the vapor dome, right? So I've drawn my vapor dome to be blue on the left-hand side up until the top of the mountain here, the critical point, and red on the way down, right? So if I'm above the blue line and to the left of the critical point, then I have liquid water, right? We call this subcooled liquid or sometimes compressed liquid. If you think about something like liquid nitrogen, it gets to be a liquid because we compressed it. We pushed those molecules together so hard that they went from being a gas to being a liquid, right? So if we're talking about water for subcooled liquids, we end up looking on table A5 in the textbook, or A5E if it's in English units, right? And don't worry, we'll get, once we meet on Thursday, we'll get a lot of experience kind of fixing states using these tables. Next, as we move over, we can be right on the line here. We could have water that's at the right temperature and pressure to boil, but it's all liquid, right? That's right on the blue line. This we call saturated liquid. So it's liquid that's ready to boil, but it's still liquid, right? So saturated liquid, probably you're going to want to find this on either table A2 or A3 if it's water. We're not going to talk about the vapor dome now. We're going to go to the other side, right? If we're above the red line here, right? So that means we're to the right of the critical point, but above the vapor dome. This means we're superheated vapor, right? Or steam. So we've boiled the water past the boiling point. So we have no more liquid left. We only have steam, and it's higher than the boiling point, the boiling temperature for the given pressure. Right? So we call this superheated vapor, and we would find this on table A4. If we're right on the line here, we have saturated vapor, right? So this means that we're still at the boiling temperature for a given pressure, but we've sort of boiled all the water, right? Now the magic for a lot of what we do happens under the vapor dome. So as we move from left to right under the vapor dome on a given horizontal line, we move from being all liquid to all vapor. So we're boiling water here, but as long as there's water to boil, we're still going to maintain the same temperature and pressure. Here we're going to use tables A2 and A3. I think I have some pictures of what these look like. I use table A2 generally if I know, say, the temperature and the quality, and I use table A3 if I know the pressure and the quality. Under the vapor dome, like we said, temperature and pressure become dependent. If you know that we're under the vapor dome, that means water is boiling. If I tell you the pressure is 1 atmosphere, then you should be able to automatically know that the temperature is 100 degrees. Or if I tell you that water is boiling at 100 degrees, you can tell me that the pressure is 1 atmosphere, right? So we need some other piece of information. And sometimes we talk about the mass percentage of vapor, right? We call that quality. So to find the quality, I take the mass of vapor divided by the total mass. So this is an example, and hopefully this starts to make it a little bit clearer, right? So here I have a temperature versus specific volume graph. And this is going to be like boiling water on a stove, but it's in a kind of a weird pot. Your pot looks like this piston cylinder assembly. There's a certain mass of the piston, right? That means that there's always the same down force, so the pressure stays constant. The pressure in this mixture, or inside my system here, is always going to be 1 atmosphere. I start here at 20 degrees, so I took out some water from the tap and I let it come to room temperature. But then I put it on the stove and I started to add heat. What happened was, not very much at the beginning, right? My grandmother used to always say, a watch pot never boils. It looks like nothing is happening, right? If you stick your finger in there, you notice that the temperature starts to increase, but you can't really tell, right? Because the volume doesn't really change very much of water, right? The specific volume doesn't change. The density stays about constant, right? So this line here, this is only a sketch. This line is pretty vertical here. The density stays about the same of water, right? But then eventually, well, first, if you're boiling water out of the tap, you get kind of this fake boiling at the beginning because the water out of the tap isn't pure water. It has some dissolved gases in it. So maybe you've noticed this. You're watching the pot and you start to see some little bubbles that form like on the surface of the inside of the pot, but it's not really boiling yet. That's the dissolved gases starting to come out, right? You're degassing the water. But if it was pure water, that wouldn't happen, right? And eventually you'd get to 100 degrees, right? And then the water starts to boil. So then in this funky pot that you have, you start to get a combination of liquid water and water vapor, right? And as you keep adding heat, what happens is you get less and less liquid and more vapor. And since the vapor takes up like 1,000 times more volume than the liquid for the given mass, the volume escalates quickly here, right? Which is the great thing about a steam engine, because that's why we boil water to make power, is because the water molecules get pushed really far apart when they make vapor, and they got to go somewhere, right? So you send them down a tube over some fan blades and get some kind of a, shaft to spin, right? So you keep adding heat here, and as you add heat, the temperature stays the same, because what's happening is those liquid water molecules, which are close together, are separating into vapor, right? So as long as there's 2 liquid molecules that are stuck together, the temperature is going to stay the same. But because what happens is, if the vapor tried to get hotter, right, then it would transfer heat into the liquid, and that energy would get absorbed by the liquid until it split apart, right? But eventually, you're going to get to the point where all of the water has been evaporated. The liquid water is all gone and it's only steam. This is the point that you absolutely never want to get to in a nuclear reactor, right? Because the water is what cools the system off, right? And what happens is, once you've boiled off all the water, liquid water is a great heat sink. It takes a lot of heat to increase the temperature of liquid water. That's why my grandmother says a watch pot never boils, because it feels like nothing's happening for a long time. But once there's no more water left, steam is a very bad heat sink, and the temperature elevates very quickly, right? So you don't want this to happen, certainly in a nuclear reactor. But even if, remember I talked about two-phase heat transfer for things like cooling off, maybe you have a two-phase cooler for like a GPU or something, right? If you get to this point, you're going to burn out your chip because the temperature escalates rapidly once you have no more liquid water, right? Because you basically don't have a heat sink anymore, right? So then you start to move over here, right? So the temperature and pressure are independent if you're all liquid, independent if you're all vapor, but dependent if you're liquid and vapor combined, right? So if you're all liquid, you can look on table A4 and A5. A4 and A5 look kind of like this, right? I apologize for the quality of this picture, but A4 and A5 are basically tables of tables. So if you knew the temperature and the pressure, so in this case, we have superheated water vapor. So we have steam. It's at 10 megapascals and 400 degrees Celsius. So what I do is I look on this table of tables until I find the right pressure, right? So here it gives me the pressure in both bar and megapascals, right? So this says if the temperature is 10 megapascals, or if the pressure is 10 megapascals, right? Remember, 1 atmosphere is a kilopascal, or is 100 kilopascals, I'm sorry, which is like a tenth of a megapascal. So this is a pretty high pressure, right? This means that water, Tsat here, this means that water boils at just over 311 degrees Celsius if we were at 10 megapascals, right? But we're at 400 degrees Celsius. That's why we're above the boiling temperature for the given pressure. So that means we're all steam, right? So then I can say, oh, I'm at 10 megapascals and 400 degrees Celsius. Those are both intensive properties. They're not dependent on the mass. And I have 2 of them, so I can fix the state. So when I know these 2 independent intensive properties, I don't just know the temperature and the pressure. I also know the specific volume, which is the volume divided by however much mass I have. I know the specific internal energy, which is what we're interested in from the first law, right? 2832.4 kilojoules per kilogram. Specific enthalpy, little h, we won't care about till after the first exam. Specific entropy, we also won't care about until after the first exam, but I can get those numbers there too. And this is nice because for this given pressure, the temperature we had is exactly a row on the table, right? Now, I could, so it's great if it's 10 megapascals and 400 degrees Celsius, because 400 is right on this table, right? But what if it was 405 degrees Celsius, right? Then I don't know what's going on in between these 2 points, right? So then we'll make the assumption that all of these properties, no matter what the property is, we'll assume that it's linear with respect to the things that we know. This is not actually true, right? They're actually all nonlinear functions. But if you're ever, you're still pretty early in your, process for getting a degree. So you'll have some choices to make in the future. Anytime you run across a class that says nonlinear something, right? So maybe you take a controls class, and then the higher level version of that class is nonlinear controls. When you say nonlinear in front of something, It means the harder version of whatever you're talking about, right? But the first thing you learn about nonlinear systems is you hope that your data points are close enough together that you can just pretend that it's linear. And that's what we'll do in these particular cases. So let's say that I had superheated vapor. I had steam, like we said, in this particular example, and it wasn't at 400 degrees Celsius, so it's still at 10 megapascals, but it's at 405 degrees Celsius, right? So I would draw a line like this, and I'd say, this was at 400 degrees. This is the next on the table, which is, I think, 440. 405 is around here. So I could draw a point over there and get a specific internal energy as a function of that temperature. Because we have almost no time left, we're not going to go through an example of this, right? But we'll start to do this next class, right? Now, there's different ways you can teach this, right? I think the way they tried to teach it to us when I was an undergraduate was to know that the equation of this line is y equals mx plus b, and then you can solve the equation. But that's a pain. And I don't want you to do it that way because there's an easier way to do it, right? So here, because this line is linear, if I know the difference between Tmin and Tmax, in that case, it was 440 and 400. So if I define some interpolation constant A as the fraction of the range that I've gone on the run of my equation, right? Rise versus run, then it's the same fraction that I've gone in the rise. That's what linear means. If you go 25% of the range in X, you've also gone 25% of the range in Y. We'll start to do problems like this next class. But it's true that this interpolation factor A could be defined as the temperature I'm looking for minus the minimum temperature in my range divided by my total temperature range, which is Tmax minus Tmin, right? That tells me what percentage of the run did I go, right? What percentage of the range and temperature did I go? That has to be the same thing for the percentage of the change in the specific internal energy, right? So if I've gone a quarter of the way with my temperature range, I have to have also gone a quarter of the way with my range and specific internal energy. So that's kind of a higher level overview of what's going on, right? But we'll talk about it more next class. So I appreciate you sticking around for 3 hours. I know it's a long class. Again, if you have some feedback on maybe how we can deliver stuff a little bit differently, we do have a lot of material to get through each class, but so you have to sort of pay attention. But I do think it's a really good idea to try to kind of watch the thermal shorts or maybe look through the notes before we get to class, because if you're like me, it's really, really hard to really pay close attention for 3 hours, right? It's probably really hard to pay close attention for 15 minutes if you're like me. So, if you can look, and even follow along with those notes, I think it could be useful. So thanks very much. I'll stick around for a couple minutes if people have questions. But otherwise, have a great night. Thanks, everybody.
Thanks so much.
You're welcome. You too.